Okay, we can also do this with addition. Inches, y in inches. Okay, you're going to come up here to 15, and we're going to cross at 7, 11, and 18. 7, 11, and 18. So my lines look like this to this to this. Okay, there's my lovely area. Find Ix, Iy, Jo, Kx, Ky, Ko. All right, first thing I'm going to do is define all of my parts of my line, okay? So I've got this first one here, this second one here, and this third one here, because I'm going to keep it continuous to the x-axis. All right, so my first one goes from 0 less than or equal to x less than or equal to 7 inches. And its equation, rise over run, is 15 over 7x plus 0 equals y. My next one goes from 7 inches less than or equal to x less than or equal to 11 inches. And it is just 15 all the way across. And then my last one goes from 11 inches less than or equal to x less than or equal to 18 inches. And it is going to be negative 15 over 7x. And its y-intercept, if we take it all the way up there, is 270 over 7. And it's equal to y. Okay, remember that's going to be if we take this all the way back up here. Okay, that's where it's going to cross. All right. Now let's plug it into equations. Ix is going to be, x is going to be on the outside, y squared dy dx, which is going to equal to, in our color coordination, the integral from 0 to 7 inches of 1/3 15 over 7x cubed dx plus red, the integral from 7 inches to 11 inches, 1/3 of 15 cubed dx plus, in green, the integral from 11 inches to 18 inches of 1/3 negative 15 7x plus 270 over 7 cubed dx. And this gives us a lovely answer of 8,440 inches to the 4th. Wolfram alpha can be your friend, right? For Iy, we also are using, okay, x-axis. So this is moment of inertia about the y-axis, but we're integrating with x-axis on the outer integration, okay? X squared dy dx. So that's going to give us the integral from 0 to 7 inches of x squared times 15 7x dx plus the integral of 7 inches to 11 inches of x squared times 15 dx plus the integral of 11 inches to 18 inches of x squared times negative 15 divided by 7x plus 270 over 7 cubed dx. And my inertia about the y-axis is going to be 15,700 inches to the fourth. All right, that means my polar moment of inertia, which is just Ix plus Iy, that's going to be, where's my final answer? 24,100 times 10 to the third inches to the fourth. Okay, I am going to need my area, which is equal to the integral of the x, y dx, and this is equal to integral from 0 to 7 inches of 15 7x dx plus the integral from 7 inches to 11 inches of 15 dx plus the integral of 11 inches to 18 inches of negative 15 7x plus 270 over 7 dx, and our area is 165 inches squared. Okay, now I know what y'all are thinking, hey, these are basic shapes and I can just use 1/2 base times height. Yes, you can. But right now we're doing everything by integrals. Don't worry, our next series of lectures are going to do simple geometric shapes with their inertia already calculated. But doing integrals makes us look real smart and mathy, so you know, that's very important. Radius of gyration x is equal to x, which is 8,440 inches to the fourth, divided by my area, 165 inches squared, square root of that, and that is going to give us 7.15 inches. My polar, I keep wanting to say polar moment of inertia. My radius of gyration in the y is 15.7 times 10 cubed inches to the fourth, divided by 165 inches squared. And that is going to give me a bigger number, 9.75 inches. And my polar radius of gyration about the origin is going to be 24.1 10 to the third inches to the fourth, divided by 165 inches squared. And that is equal to 12.1 inches for that value.